Honorable members of the jury and distinguished audience, it is my pleasure to present the results of the research in order to obtain the PhD degree from University of Lyon. This work was carried out at the SuperGrid Institute in partnership with the Ampere Lab, under the direction of Guy Claire and Emmanuel Boucleux from Ampere Lab and François Wallard from the SuperGrid Institute. First, to give some context on this work, we have to know some of the characteristics of HVDC. HVDC transmission systems don't have any frequency-related disadvantages, so there is no need for a reactive compensator and there is no skin effect. This allows for the use of longer cables. Also, HVDC transmission systems enable the interconnection of asynchronous AC grids, and they are the preferred technology for performing bulk power transmission over long distances. On this slide, we can see an example of an HVDC link connecting an offshore wind farm to the mainland. What are the motivations behind this work? According to the European Network of Transmission System Operators, the levels of HVDC system availability and reliability are not fully adequate. And inside the HVDC transmission systems, the converter stations are one of the main assets that play a role in system reliability. The previous technology used up until that point for the power converter stations were line commutated converters. And now the new European projects are mostly based on the modular multilevel converter, which has also some particular challenges regarding the reliability of the system. Now, if we go into more detail into the MMC structure, we can see that it is a converter composed by legs, which themselves are composed by upper and lower arms, which contain stacks of submodules and an arm inductor. The submodules used in this structure, the most typical topology employed is the half-bridge submodule, which has two switches that enable the insertion of a capacitor into the main circuit. This topology is completely scalable, as the submodules can be connected in series to attain the voltage levels required by the HVDC application. This type of structure also eases the constraints on the series connection of switches, and the output voltages seen on the AC and DC sides of the topology are controlled by the insertion or the bypass of the submodules present. It is worth noting that in a typical HVDC application, the number of submodules can be really high. We can have numbers of 400 submodules per arm, which in the end gives this topology low harmonic content and a reduced switching frequency for each of the individual submodules. Now, if we see a submodule structure, we also need to mention that the submodules can be bypassed in case of internal defaults in their structure. The faulty submodules are bypassed and the arm can still be operational if we have installed redundant submodules that allow for continuous operation. Now, if we go into detail in the half-bridge submodule, we see here an image of this structure. It has the storage capacitor and a power electronics block. And inside this power electronics block, we have the IGBT modules that are one of the main elements from an operational point of view. In previous research works, the reliability of capacitors has already been studied in the context of MMC. And also, IGBTs are considered to be the most fragile elements in the power conversion chain. Therefore, this work will focus on the IGBT modules. The IGBT modules used in the MMC application, the flat pack technology is still relevant in the HVDC application. This type of technology is composed by layers of different materials, which purpose is to perform the electrical connections of the IGBT chips to the exterior circuit, and also to cool down the chips that perform the power conversion. The different layers are composed by different materials, And this type of technology can experience sudden or progressive failures, and only progressive failures can be tracked for assessing the state of degradation of the modules. These types of failures are associated with the degradation of the packaging themselves and not of the semiconductors. Some of the main weak spots are the bond wires and the solder layers. And progressive failures are mostly associated with the thermal stress due to the mismatch of coefficients of thermal expansion between the different materials inside the structure. With this in mind, we have set two main objectives. The first one is to verify the impact of the environment and the operating conditions on the reliability of the converter. And the second one is to develop a condition monitoring technique to assess the state of degradation of the modules. Having this in mind, we propose the following agenda for tackling these objectives. The first part will deal with a more theoretical study at the converter level, and from this study, we have performed lifetime estimations and we have performed reliability calculations. This first part has evidence that the IGBT is a critical component and its thermal loading can have a major impact on the converter. Therefore, the second part will deal with the health monitoring of this element. And for this purpose, a power cycling test bench was built. And we have performed the calculation of the junction temperature and the degradation of the semiconductor for this part. Finally, some conclusions on the results obtained will be made. Now, let's proceed with the first part, which is the MMC lifetime estimation. What are the motivations behind this work? Now, there are projects, for example, the multipurpose interconnector, in which a converter station that was supposed to perform the connection of an offshore wind farm to the mainland can also be connected to another neighboring converter station in order to allow the interconnection between two different countries. Therefore, the mission profile of the converters is also subjected to change. Then we want to address this subject by measuring what's the impact of this mission profile change on the lifetime of the converters. And also we want to know how the operating conditions can affect the reliability of the semiconductors themselves and of the converter. One of the main stressors, as mentioned previously, is the junction temperature. Therefore, we wish to specifically address what is the effect of the maximum junction temperature on the reliability. For performing the lifetime calculations, we have developed a methodology. In the first stage, we calculate the losses from all the semiconductors present in a submodule. And this stage uses the emission profile and the junction temperature as the main inputs. The second stage consists on the thermal modeling, which takes the losses and also the ambient temperature for computing the junction temperature. Then we use cyclone counting methods that allow to organize the thermal profiles, which allow finally the use of lifetime models for calculating the lifetime consumption. It is worth mentioning that this methodology is well known in the literature, but we have made some adaptations to make it compatible with the modular multilevel converter. Once again, the thermal stress is the main source of lifetime degradation. Now for the first part, which is the calculation of the losses, we see that this stage considers two other previous steps, which are the converter modeling and a device loss model. As mentioned previously, the inputs of this stage are the junction temperature of the devices and the converter operating point. We have obtained 3D lookup tables for all the semiconductors present in the submodule to compute the losses as a function of the operating point. It is worth reminding that the converter model is a hybrid model because we require the waveforms just for a single submodule. And two of the legs of the converter were simulated with a classic average model, and the third leg was simulated with a detailed model. also it is worth noting that we have used the datasheet information for computing the losses in this step. Then for the thermal modeling part, we have developed two different thermal models because we are focused on two different timescales. In the first type of thermal model, which is a static thermal model, we don't consider any heating dynamics, and this model is used for time steps of 10 minutes with a time span longer than 1 year. The dynamic thermal model has lower time steps in the range of 1 second, and the time spans are less than 10 minutes. The static thermal model developed was used for the long-term timescale, and the dynamic thermal model for the medium-term timescale. Now, for the cycling counting part, what is the objective of a cycling counting algorithm? We take a raw temperature profile, and we wish to identify the thermal cycles present within this temperature profile. We wish to identify thermal cycles that are characterized, for example, by an average junction temperature, a junction temperature variation, and a duration of a cycle. Therefore, these counting methods identify the low frequency cycles present in the temperature profiles, and also they identify the high frequency cycles present within them. With these counting methods, we have an overall summary of all the different thermal cycles present in this profile. Here we can see an example of a long-term thermal profile of a semiconductor and the corresponding rainflow histogram. Here we can see that at an average temperature of 40 degrees and a thermal variation in the range of 5 degrees, we have a high count of thermal cycles. Once again, the main goal of this type of algorithm is to identify the thermal cycles within the profile. Once we have obtained the organized thermal profile, we can then use the lifetime models provided by the manufacturers. They take the main parameters organized by the rainflow counting algorithm, such as the variation of the junction temperature and the maximum junction temperature, to compute the number of cycles to failure for a given particular thermal cycle. However, manufacturers don't recommend using their lifetime models, outside its boundaries. Therefore, we have developed a special method for interpolating and extrapolating the lifetime models provided by the manufacturers by using the Norris-Landsberg model. Then the lifetime consumption of for any given particular thermal cycle can be computed by dividing the number of experienced cycles for this condition and under its number of cycles to failure. And the total lifetime consumption can be computed by adding all the lifetime consumptions of the individual thermal cycles. As mentioned previously, we wish to address the different types of emission profile seen by the converter. Therefore, we want to address the case of a point-to-point application and an offshore wind farm. In the case of the point-to-point application, the HVDC link data is directly used as the power set point for the converter, which will then be used as the entry for our lifetime estimation methodology. In the case of the offshore wind farm, we will take the wind profile, and as an intermediate step, we will calculate the corresponding operating point by using a turbine model, and therefore we will be able to use the same lifetime estimation methodology. Here, just as an example, we see the raw temperature profile in the case of the long-term analysis. We have wind speed data every 10 minutes. And with the help of the wind turbine characteristics, we have computed the power set point for the converter. It is also worth reminding that the power reference comes from a turbine characteristic. And the different types of wind turbine models were used in the long-term and medium-term timescale. As for the lifetime consumption results, we were first interested in to see the effect of the emission profile on the lifetime consumption. Here we see a comparison between the point-to-point application and the offshore wind farm application. The lifetime models used contain the lifetime models for the different elements within the semiconductors, such as the chip solder, the substrate solder, and the bond wires of the semiconductors. And we have calculated the lifetime consumption for each of the semiconductors. We see that IGBT2, the lower IGBT, is the element that suffers a higher lifetime consumption in compliance with previous research done on this topic. And we see that also the lifetime consumption on the offshore wind farm application is almost twice in some cases compared to the lifetime consumption in the point-to-point application. Another point that we wished to address in this work was to compare the maximum junction temperature allowed for the semiconductors. Therefore, here we can see a comparison in the case of an offshore wind farm application. And it is evident to see that working at reduced junction temperatures allows to improve the lifetime consumption by a factor of 10 when compared to a maximum junction temperature of 125 degrees. Now, this lifetime consumption methodology has allowed to perform the reliability assessment for the health management of the converter. What are the motivations behind this work? We wish to answer the questions: how many submodules does an MMC use throughout its operating life? We want to know how many redundant submodules are required for achieving a target availability. And we want to know what would be an optimal maintenance strategy for the replacement of the submodules. Therefore, it is worth studying how this lifetime consumption can be translated to a reliability distribution. If we know that the lifetime models employed give the B10 lifetime, which represents the number of cycles to failure for a cumulative failure rate of 10%, or the number of cycles to failure for a non-reliability of 10%. Therefore, the lifetime consumption results can be translated to a time by which the unreliability of the semiconductors or the elements within the semiconductors will be of 10%. Here we'll illustrate this with a very simple example. If we have a B10 lifetime consumption of 50% and we have studied a profile of 1 year, this means by 2 years, we will have an unreliability of 10%. Normally, the unreliability distribution is modelized with the help of the Weibull distribution. This distribution is characterized by the shape factor beta and the failure rate lambda. And there are many different possibilities that can be a solution to this particular point of interest. Therefore, if we will focus ourselves on the bathtub curve, which describes the phase of a product in terms of its reliability. When we have a shape factor of 1, this represents that an element is at the phase of its useful life. There is only random failures in the system. And if we have a shape factor higher than 1, this means that this element is suffering from a higher degradation. Therefore, we will focus only on the two stages when we see the useful life and the wear out phase of the elements. Now, for the reliability predictions, we know also that the reliability can be computed from the unreliability of an element. We also know that the unreliability of a system can be computed from the unreliabilities of its composing elements. And here we can see the results for the elements within the semiconductors, from the semiconductors themselves, and also the reliability of the submodule, which was computed from the reliability of the semiconductors, and also the capacitor and the electronics present in its structure. The results seen on the screen were computed with the shape factor 2.5, and these values will be retained for performing converter level predictions. In the case of the redundancy computations, we know that there exists a traditional approach that does not consider the replacement of faulty submodules. This approach uses the binomial distribution and assumes that all the submodules present in the structure share the same probability of failure or the same probability of survival. However, we have seen in the first part of the presentation that faulty submodules can be bypassed, so therefore they can be renewed at following maintenance intervals. Therefore, we have developed a new approach that considers the replacement of the faulty submodules at the different maintenance intervals, and also allows to evaluate the reliability of the converter by the end of its target mission life. In this case, is set to 40 years, and the new approach is based on the use of a Markov chain. In the Markov chain developed, at each maintenance interval, a submodule has a probability of failure and a probability of survival. If a submodule has failed and the number of failed submodules is inferior to the number of redundant submodules installed, then the submodule is replaced by a new one, and its probability of survival is reset to 1. Therefore, we take into account the renewal of the system. However, if a submodule has survived in between two maintenance intervals, its probability of survival for the next interval is conditioned by the fact that the submodule has already survived the previous maintenance interval. Here we can see some of the results obtained with the Markov chain approach. Here, the results represent the number of redundant submodules per arm. We have already mentioned that a submodule uses 400 submodules, and we see that the resulting number of redundant submodules is in the range of 23 to 26 submodules. The case study set an arm reliability target of 99.5%. With a maximum junction temperature of 90 degrees and a time between maintenance of 2 years. We see from this result that there is a low sensitivity to the variations of the shape parameter beta. In terms of submodule replacement and usage, the methodology developed has also allowed to evaluate the number of submodules consumed by the arm, because we can simulate also the failures between the maintenance intervals. We can see on the left-hand side of the screen that we have computed the number of failed submodules between two maintenance intervals, and this has allowed to calculate the number of total submodules employed by the MMC arm. We were aware that we required only 400 submodules for the operation of the arm. We required 23 redundant submodules for attaining the target reliability. But by the end of the mission life of the converter, we will have used more than 630 submodules in total per arm. We have to be aware that this structure has 6 arms in total, so there is a really high count of used submodules in this example. Also, we can see the summary of all of the case studies in terms of mission profile and junction temperature, and also the shape factors. We are aware that the most stressful case is the offshore wind farm application, and that junction temperature of 125 degrees is also one of the more stressful. For this case, we need 31 redundant submodules in the arm, and the usage of submodules throughout the operating life of the converter will be of 740 submodules. This Markov chain approach has also allowed to evaluate different types of maintenance strategies. What is the goal of these maintenance strategies? Normally, we replace only the faulty submodules in between two maintenance interventions. But the purpose here is to see if another type of maintenance strategy can allow to reduce the number of redundant submodules installed and the total usage of submodules. For example, here, the hypothesis was that if we would have replaced 25% of the oldest submodules at half the mission life, we would have renewed the system to a point in which there is no so much failures by the end of the target mission life. However, the results indicate that only replacing the faulty submodule seems to be the optimal strategy in terms of submodule usage, and that other strategies can help reduce the number of redundant submodules. However, the count of submodules employed throughout converter operation will still be higher. Some of the takeaway points for this first part of the study are that we have used a traditional methodology for performing lifetime consumption, and we have adapted it for the modular multilevel converter by using a hybrid converter model, and that we have also used a model-based method for using the lifetime models of the manufacturers. We have seen that the emission profile and the maximum junction temperature can have a high impact on lifetime consumption and on the reliability predictions. We have developed a method for computing the usage of submodules, and it also takes into account the emission profile of the converter, and it employs Markov chains and Monte Carlo simulations for this purpose. And we have compared different types of maintenance strategies for the replacement of the submodules. Now we will proceed to the experimental part of this work, which deals with the IGBT health monitoring. We have developed a power cycling test bench for performing this type of study. What are the goals of the test bench developed? We wish to perform accelerated lifetime testing under realistic conditions. We wish to develop lifetime models based on the power cycling data. We want to build an IGBT degradation database that will be used for database methods of lifetime prediction. We want to define suitable degradation-sensitive electrical parameters that will help track the degradation of the IGBT devices. In order to carry out these tasks, it is also important to know what a cycling protocol should look like. Here we see that we require different types of characterizations or measurements for performing this protocol. We have the need for performing characterizations for updating the thermal models, because we are interested in knowing what is the junction temperature of the devices. We wish to carry out these characterizations at 3 stages throughout the cycling protocol. These types of characterizations involve the computation of the output characteristics of the semiconductors, the computation of the thermal impedance, and also computing the switching energies for calculating the losses. Also, we want to perform characterizations for health monitoring of the device. In this case, we perform characterizations that require to stop the converter operation, and these types of characterizations will be carried out once a day with the help of a source meter unit. We also want to perform continuous tracking of the state of degradation without interfering the operation of the converter. For this purpose, we want to stream data from the converter. In this case, we will stream 10 seconds of operation every 10 minutes. This was carried out with the help of a monitoring board that we have developed. And some of the measured parameters of this board are the on-state voltage, the collector current, the junction temperature, and the case temperature of the semiconductors. Therefore, we can see here the overall cycling protocol and all the measurements required for performing the assessment of the state of degradation of the devices. Also, it is important to know, before applying a power cycling test, which are the cycling conditions that we want to address. In this case, we are basing our test plan on the lifetime models existing in the literature, in this case, the Bayer lifetime model. This model calculates the number of cycles to failure based on many different parameters, but the parameters of interest that we want to address are the variation of the junction temperature, the minimum junction temperature, and the heating time. Therefore, we have proposed a plan in which 8 different tests will be performed. 3 of them will verify the influence of the variation of the junction temperature and will aim to recalculate the parameter that affects this value on the lifetime model. 3 of the testing plans will be used for verifying the influence of the heating time and also its parameter. And other 3 tests will be used for verifying the influence of the minimum junction temperature. Finally, a test plan is proposed for validating all the prognosis algorithms and the estimation of the number of cycles to failure. In terms of the topology to be used for the power cycling tests, in the literature, we see 2 main families, a DC power cycling circuit and an AC power cycling circuit. They are different in topology. In the case of the AC power cycling, we have a much more complex complex structure. The waveforms used for performing the cycling protocols are also very different. In the case of DC power cycling, we traditionally apply the square waveforms. And in the case of an AC power cycling circuit, we impose a sinusoidal waveform to the inductive load present in the circuit, which causes the heating of the devices. However, we have decided to retain the AC power cycling topology, as it imposes a more realistic stress to the device under test, as it experiences conduction and switching losses. Now, here we can see an overall schematic of the power cycling circuit developed for this study, which is much more complex than the regular H-bridge configuration. This structure has several elements for performing the control and the protection of the circuit, since we wish to go until the failure of the devices under test. And also we have installed dedicated hardware in order to perform the surveillance of the state of health of the device under test. In our structure, only one of the half bridges of the structure will be considered the device under test. Here we can see a picture of the power cycling circuit with its main elements, and we can see that the device under test can be easily replaced and can be easily removed for performing all the characterizations mentioned previously. The overall test setup consists of 5 identical converters in order to parallelize tests and be able to perform statistical calculations in terms of the aging of the semiconductor devices. And here we can see an overall representation, a picture of the implementation of this power cycling test setup. The control strategy chosen for this for the power converters consists on an open loop voltage reference for the DUT branch, and the current across the inductive load will be controlled with the help of a closed loop controller and a PI controller. The current across the inductive load will give the thermal characteristics of the thermal cycles imposed for the aging of the modules. The variation of the junction temperature will be obtained with the peak current through the load and also with the switching frequency of the IGBT devices. The heating time is computed with the output frequency of the current. The minimum junction temperature is controlled with the help of an external chiller. Another particularity of this test circuit is that the power factor can be used either for stressing the IGBTs or the diodes on the DUT branch, and also that each converter has an independent controller, which allows to perform phase shifts between the different converters in order to reduce the losses coming from the DC voltage source. For time purposes, we will only describe the main board that we have developed for performing the health monitoring of the devices under test. This board was meant to perform the measurements of the on-state voltage. We know that the voltage across the collector emitter terminals of a semiconductor device can have a high blocking state, in the case of our study, in the range of 600 volts. And the voltage of interest, which is the on-state voltage, that has a really small value compared to the blocking voltage. So we want to implement a circuit that saturates the high blocking voltage. And the output that we fixed is in the range of 7 volts when we are at the high blocking state. And we will have the on-state voltage at the measurement terminal once we are at once we have a low voltage across the collector emitter terminals. Also, this circuit is an improvement from circuits already proposed in the literature and can measure either the collector emitter voltage across the IGBT and the forward voltage across the diode, and is also compatible with fast switching semiconductors. Also, it is important to know that in order to be able to track the degradation of IGBTs, we require a precise measurement of the on-state voltage in the range of 1 millivolts Therefore, the measurement board developed uses 18-bit ADCs for obtaining the required precision. We also know that one of the advantages of measuring the on-state voltage is that we can deduce the junction temperature if we also have the collector current across the semiconductors. Therefore, our measurement board also performs the measurement of the phase current in order to determine the collector current of the devices. And we know that it is risky to perform the measurement of the high side on-state voltage, as it has a floating reference. Therefore, we have used optic fibers in order to insulate the subsequent measurement stages in order to not damage them by performing the measurement of the high side on-state voltage. The overall result is the measurement board seen on the screen. As for the junction temperature estimation, we have already seen on the MMC portion of this work that the junction temperature has a major impact. Therefore, we wish to know what is the real junction temperature of the devices in the case of our power cycling circuit. The motivation is that the knowledge of this temperature is crucial for IGBT and reliability assessment, and that if we want to perform power cycling tests, we really want to know that we are applying the correct thermal cycling condition. We also know that indirect measurements from the junction temperature can be obtained from the IV characteristics of a device. Here we can see an example where we have the output characteristics, but we see that near the crossover point, we cannot really distinguish which is the junction temperature. Said otherwise, we can see that we have a really good estimation of the junction temperature when we have high current. Therefore, this method is not well suited for performing the measurement of the junction temperature at low currents. Also, we know that estimations of the junction temperature can be obtained from thermal impedance models. But in this example, we can see the difference between the thermal model provided by the manufacturer, which is the red curve, and the thermal model obtained with a characterization device. The conclusion is that models always have biases and that they require a feedback in order to validate their outputs. Therefore, we have set ourselves the goal of using a Kalman estimator for taking the advantage of both methods, from the measurements and from the estimations coming from a thermal model. Now for the Kalman filter, it is an optimal state estimator, which fuses the information coming from a measurement and the model to give an accurate estimation of a state. In this case, we don't use a direct measurement, we use an indirect measurement, which comes from the measurement of the phase current and the collector emitter voltage. The first phase for applying the Kalman filter is the computation of the losses. For this purpose, we take the readings coming from our BC board, the on-state voltages from the high side and low side switches, and also the phase current, to calculate whether a semiconductor is at the on-state. Then we perform algebraic calculations, and we use also a lookup table that has the switching energies for all the semiconductor devices. The second stage was the indirect measurement. From a pair of collector current and on-state voltage, we compute the junction temperature. We require also the knowledge of the case temperature of the devices. For this purpose, we have installed PT1000 sensors on the interface between the base plate and the cold plate. And we use a 4-layer Foster thermal model for the computation of the thermal model. As we mentioned previously, indirect measurements are accurate at high currents. Therefore, we use a Boolean variable A in order to consider the indirect measurements if we are at a higher current than the defined threshold. Even though the Kalman filter is a good estimation tool, there are still some challenges in order to be able to use it with a high precision. Its performance depends notably on the calculation of the Kalman gain, and the computation of this gain also requires the knowledge of the noise matrices present in the system. In most of the cases, these values are unknown. Therefore, we have used the autocovariance least squares method in order to parameterize the Kalman filter. The stages of this method is to use first a Kalman filter with an arbitrary Kalman gain, which yields a non-optimal estimation. Then the residuals obtained with this non-optimal Kalman filter are retained for a large number of iterations. And from these residuals, an autocovariance matrix is constructed. Finally, the estimated values of the real covariance matrices are obtained by solving an optimization problem involving the autocovariance matrix and the original thermal model used in the Kalman filter algorithm. Once we have obtained the estimated Q&R matrices, we can compute the optimal Kalman gain. Here we can see the validation of the estimations obtained with the Kalman filter. In order to carry out these validations, we required a real measurement of the junction temperature. For this purpose, we have installed fiber optic sensors in direct contact with the IGBTs present in the IGBT modules. Here we can see how we have installed ceramic guides for placing the fiber optic sensors. And we can see that the Kalman filter agrees, it has almost the exact dynamics as the fiber optic sensor employed. And we can see just a small difference between our Kalman estimation and the real measurement obtained with the fiber optic sensor. This difference is in the range of 1 degree, which is already acceptable by some standards. Finally, for the degradation assessment of the state of health of the IGBT devices, one of the purpose was to study different degradation sensitive electrical parameters. We have retained some DCEPs that were obtained without interfering the converter operation with the help of our BC board. Some of these DCEPs are the on-state voltage at different current values. We have evaluated currents below the crossover point, above the crossover point, and at the crossover point. We have also used the Kalman estimation of the estimated junction temperature as a DCEP, and also the ratio between the variation obtained with the Kalman estimator and the variation obtained with a simple thermal model. This ratio should be proportional to the variation of the thermal resistance of the IGBT devices. From all of the proposed DCEPs, we have retained the on-state voltage at the crossover current, which seems to be the most suitable among the ones we have mentioned previously for tracking the degradation of the devices. Here we can see one of the 10-second streams of data in which we have the measurements of the on-state voltage at different current values. Here we can see the value at the crossover current, and we compute the average value in this stream of data. And on the right-hand side of the screen, we can see the evolution of the on-state voltage throughout the power cycling protocol. We see that there's an evolution of this value, and we have performed the power cycling tests until the failure of the device. We can also see that somewhere around 70,000 cycles of operation, there's an important jump in the value of the on-state voltage, which can be related to the degradation of the internal layers of the device. Finally, we have performed a postmortem analysis of the cycled modules. For this purpose, we have opened the modules and removed the silicon gel. And a visual inspection has confirmed the bond wire liftoff of the studied devices. The takeaway points of the second part of this presentation are that we have successfully developed an AC power cycling test bench. We have developed a monitoring board for performing the health assessment of the devices. We have developed a method for estimating the junction temperature of the IGBTs and also for parameterizing the Kalman filter. We have successfully tracked the evolution of the DCEPs that can give an estimation of the state of degradation of the semiconductors. Now, for the conclusions of this work, regarding the initial objectives, We have verified the impact of the environment and the operating conditions by analyzing, by using a traditional methodology for lifetime consumption, using a special method for the interpolation of lifetime models. We have computed the effect on the internal layers present in the semiconductor devices. We have developed a methodology for accounting for the number of submodules used throughout the operating life of the converter, and we have obtained the total submodule usage. Regarding the objective of developing a condition monitoring technique, we have built the power cycling circuit. We have developed hardware for performing the tracking of the state of health. We have performed the accurate junction temperature estimations, and we have tracked the evolution of DCEPs. Some of the perspectives of this work: in the short term, we wish to finish the proposed testing plan, as due to time constraints, we weren't able to do so. We wish to use other DCEPs to improve our estimations of the state of degradation, and we wish to validate and to build new lifetime models. The perspectives on the long term are to extend the methodologies developed on this work to other types of devices, such as diodes or wide bandgap devices. We also wish to combine the remaining useful life information obtained from the thermal loading of the devices, along with the drift of DCEPs, to give a more accurate estimation of the remaining useful life. And we wish to assess the impact of other types of stressors, such as humidity, to perform multidimensional stress analysis. Thank you very much.